Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you guys are doing good. In this, we're going to see about minimum cost to make at least one valid path in a grid. Now, if you would have watched our previous videos, again, I'll not give more of spoilers, but you should be able to at least think of this easily. Now, let's start off. It simply says that we are given an m cross n grid. As you can see, I'm given a specific grid of size m cross n. Now, each cell of a grid has a sign pointing to the next cell you should visit if you're currently in this cell, and the signs are 1, 2, 3, 4. So basically, as an input, you will see that you are given the values 1, 2, 3, 4 as the grid values. What these values actually represent is one value represents a arrow, which is a right arrow. What this arrow actually mean is that from if the arrow is here, then you can easily go on to the next cell. Let's say if the arrow is down, if the arrow would have been down, then you can easily go to the down cell. This is what the actual arrow means, that you can go to that specific cell without doing any effort. Easily go to that cell. Like if the value is 2, which means the arrow is left, which means you can go to the left cell easily. If the value is 3, you can go to down cell. Value 4, you can go to up cell. So as you can see, this is value 1. As you can see, value 1, you can easily go to the right cell. Value 1, easily go to the right cell. This indicates that you can go to the next cell. Now that next cell direction will be right, left, up, down, will be dependent upon what the value there is. Now, notice that there could be some signs on the cell of the grid that point outside the grid. As you can see, this indicates that you can go right, but write it outside the grid. So they are also saying that, okay, you can have some cells which can also make you go outside the grid. So make sure that part. And I'm initially at the start cell, which is 0, 0. I'm initially here 0, 0. Now, a valid path in a grid is a path that starts from the upper left cell and ends at the bottom right cell. Following the signs on the grid, the valid path does not have to be the shortest path. Okay, so they are saying any valid path, give me any valid path. This is, let's say, could have been a valid path for me, considering this arrow would have been down, because from here he's asking me to go left, but I want to go down. So again, you just have to get him any valid path such that from top left to bottom right you are able to go. Now, as you can easily see that in the current configuration, you are going here, then okay, he is letting you go outside, but you want to go downwards. Your destination is here. So you, let's say, change this cell. Let's change it. Yeah, you change this cell to, let's say, this. Then you came down. You did one change so far. Then he's asking you to go left. Okay, let's say you change this. You can again come down. He's asking you to go right. Okay, you can again change this and you can come down. Yes, you have now reached the final destination. How many changes you did? The cost or the minimum cost or the minimum changes are actually 3 to reach the final destination. And you can try for multiple possibilities. You will see that you are able to reach the final destination in you will have to use at least 3 changes. Okay, let's see a different example. Here I'm going here. As I go on to here, I can also come down. Okay, I can come left, I can come down also, I can go right, and I reach here. Oh, I did not have to do any change. Answer is 0. Okay, let's go on next one. Here if I go right, oh, I have to go down technically, so I have to change here and I will come here, which means one change required. Answer is 1. Okay, awesome. Now you must be thinking, Aryan, as I have to start from the top left, I have to reach bottom right. It gives me vibes of DP of grid, like DP on grids. But if you don't know, I have always asked you that DP of grid is applied in the scenarios where you are starting from one cell and you have only two operations, either go right or down, right? Which means that you are going like this fashion downwards towards here. But because of this configuration which you have right here, you could actually end up going down, then right, then up, anywhere you can go. Thus, it is not more of a DP on grid problem, but is more of a DP on, sorry, it is more of a graph problem, that you are given a grid and you have to traverse on that grid. Now, so one thing again, if you don't know about DP on grid, you can just go and simply watch this video. You'll get the idea of DP on grid. But even if not, Let's say take any standard situation and any random situation. Let's say I am here. My arrow is pointing to the right side. Imagine the current cost to reach at this location. Again, when I say to reach this location, imagine that it is coming from somewhere at the very top. Why I am telling you this is because anywhere you have to think of what should be the answer. Always don't start off from the very scratch and do a proper dry run. This is actually a very BS thing to do. Considering you know the basic of grid or anything whatsoever, always start off from a random location. Okay, let's say a middle location. Now imagine the cost here to reach would have been C. Now, to go to the next specific location, as the arrow is directly pointing to that location, the cost will be same C. But as you know that there could be possibility, what if I go up and then there could have been a different better path and then I would have been able to reach in a lesser cost. So I will also say, okay, to go to the up, I'll have to change the sign, which means plus one added, right? Same way, I have to change a sign to go back, plus one added. Same way, I have to add a sign, plus two, like plus one added. So what we realize is from this cell to go here, I can easily figure out the corresponding cost. Now, if you would be thinking, okay, I will simply apply a DP, which means that to reach at this point, what is the corresponding cost? Okay, good that you are thinking of DP, but as I already mentioned, that to reach at this point, let's say if you would have, say, okay, DP of ij, you might end up visiting the cell from different paths again and again. Because, okay, let's say this is a start point. What if one path would have been something like this, another part something would have been like this, another part something would have been something like this. So, and again, this is just to reach this specific point. Now from here you would be going to some different path. There can be multiple such paths. That is the reason if you end up applying DP, obviously you would incur a complexity of m into n for sure, but along with it, m into n again, and even if not, again, firstly, it will be very hard to prove whatever algorithm you write. Let's say if you write any algorithm, firstly, it will at least incur m into n whole square time at least. Apart from it, on the basis of what algorithm you are writing, especially for DP, it will also can increase. That is the reason it is actually a bit skeptical to actually, just forcefully apply DP here. Thus, we also realized one thing, that technically I'm just exploring the corresponding path. Like for one cell, I'm just exploring its corresponding neighbors. Then you might feel like, okay, Aryan, I can simply apply a BFS. But again, the same question, that you're applying BFS or maybe again BFS along with DP, then how many times? That's a big question. That how many times? So isn't it that I'm only concerned about minimum cost? So let's say if I'm able to reach here, I am able to, let's say, reach here by this path, I'm able to reach here by this path. Why do I have to consider, let's say when I say this path, which means that to reach here at this path, the cost would have been 3. Let's say to reach here via this path, the cost would have been 2. To reach here via this path, the cost would have been 5. Now, from this point, if I have to start exploring again, then why I should even bother about exploring this and this? Isn't it that I should only explore starting from point C if I only explore forwards? Because I'm only concerned about the minimum cost. So isn't it the problem now going towards that you are starting from a cell, you have options to explore your neighbors, and you always have to choose the minimum cost path. So isn't it that you are going towards Dijkstras? You're just simply exploring neighbors, which is kind of, exploring BFS, but at the same point you have to make sure that you are taking the minimum cost path, so that you are always trying to explore minimum cost, and if you reach the end, which is m minus 1 comma n minus 1, then it is good to go. So that is the thing, that I can simply apply Dijkstras here, which is very straightforward, completes my purpose. Now, let's see how actually we can write Dijkstras. Again, if you don't know what Dijkstras is, simply go and watch Dijkstras video. I will not explain what Dijkstras is here. Now, if you know what Dijkstras is, obviously, I will have to maintain, basically Dijkstras maintains a priority queue. Priority queue needs something that what it is maintaining. Obviously for me, the first priority is, okay, get the cost. That is the only thing. Minimum cost point should be, traversed first. But cost is independently will not help me go to the neighbors. I also need x comma y to go to neighbors. That's the reason my priority queue will maintain cost x comma y. Now obviously, whenever I will simply traverse, I will need directions. I will go to 4 directions. That is, I will maintain the corresponding directions for me. Then I, that this is a grid. This is the grid. And I also made sure that I will go on to a specific cell only and only when the cost to reach there is minimum or lesser than the earlier cost to reach there, right? So I will also maintain a cost array. No worries, I'll explain you what this is, but I'll maintain a corresponding cost. Again, that actually it's a grid, so it should be a cost array, a vector of vector. Okay, then obviously I will have to maintain a priority queue. Make sure this is simply your min heap, right? So as to get the minimum corresponding cost. Now, in the very beginning, I will simply push inside my, this specific priority queue. I'll simply push up 0 0 0 minimum cost. Like in the beginning, cost is 0, x comma y is 0. And also I will just update my cost, that cost for 0 comma 0 x comma y is 0. Then as you simply do in a priority queue, while the pq is not empty, what you do, you simply say that firstly get me out the current element. So I'll get the current cost, I'll get x, I'll get y, and I will simply, you know get there from the priority queue. And then also make sure to remove the elements from the priority queue. Now when this is done, you have to make sure that you can actually go on to that specific cell with this cost, because again this is saying that for the cell x comma y you are going with this current cost. But what if the cost to reach here, which means the cost to reach x comma y, if the current cost, if it is more than the cost to reach x comma y, obviously it's of no use because already you have reached x comma y with a lesser cost. Then simply continue and try for the next thing in the priority queue. If not, then obviously you can simply say, oh Aryan, I'm able to reach that specific cell, so just simply try for your neighbors and just going on to all the 4 directions, that dir is less than 4 and dir plus plus directions, and then go and find the new x, which is nothing but x plus corresponding directions, and find the new y, ny, corresponding y plus the corresponding directions, whatever you have. Make sure that you have a very base condition, that it is inside, which means nx if it is less than 0, or nx if it is more than equals to m, or ny, same way. If it is going outside, simply continue because you should not go outside. If not, then find the new cost, let's say nc, new cost. That will be nothing but the corresponding current cost which you have, right? Current cost which you have plus now the cost. Obviously we realize that for this cell, let's say x comma y, this is a cell and this is the current cost, this is the current cost. Now I am going on to the next cell, which is the new neighbors I am going on to. I told you that if this direction is the same, then this new cost will be the same, current cost. But here new cost will be current cost plus 1. Here the new cost will be current cost plus 1. Here the new cost will be current cost plus 1. That is the reason current cost will be there. Obviously current cost is there, but new cost will depend upon if the direction, if it is not equals to my this value, grid of x comma y. Now just a bit nuance, you will see in my code that direction here is the actual direction, which is this 0 to 4, while in the input the grid values represents 1 to 4. It is minus 0 to 3, while the grid is 1 to 4. That is the reason I'll do a minus 1, just so as to be in line with the input. Okay, now I'll simply say that if my new cost If it is less than the cost to reach new cell, which is new x and new y, then make sure to update your corresponding new x, nx and ny. And then again, when I say simply updated, update it with the corresponding new cost, nc, and make sure to put this in the priority queue. Simply in place it. You can do push also, that new cost, new x and new y. And awesome, now you are like, now you have simply done it. So you see that you're only pushing up the corresponding new x new y only if the cost itself is less. And this is kind of a proving, again there are multiple ways to approach a priority queue or a Dijkstras problem, but this will make sure that already the cost is minimized, such that next time if I go up, next time if you're encountering a cost which has already been inside the priority queue before, that if it is coming again to actually go and explore its neighbors, it will not be explored. Now again, this is a very high level of Dijkstras which I have told you, but again, just because to show the code. But if you want to learn a low level, please go and watch this video of Dijkstras. If you don't understand Dijkstras, that's the reason. Now coming on, what is the complexity for this? Obviously, as you are going on to every point inside the corresponding grid, m into n will always be there. But for every point, what you are doing, you are simply, for every point you are simply checking your priority queue and correspondingly also pushing an element in the priority queue. Now complexity of priority queue depends upon what all elements are already there in the priority queue or what can be there in the priority queue. Now to reach any specific cell, right, let's say if I reach this specific cell, there are four ways I can reach here: from left, from bottom, from right, from top. Which means that a specific cell, again, a specific cell in worst case can only be pushed at max 4 times inside my priority queue, which means that the complexity will be 4 into, again, log of 4 into n, because the priority queue size can at max become this, although it will be much lesser than this. But still, why I'm saying at max, just so as you can understand how a point can be pushed in. A point can be pushed in if it is coming, let's say if the path is coming from left, okay, the path is coming from bottom, maybe from right, maybe from up. Now you might ask, Aryan, why not it can be repeated, which means that, okay, let's say if I come from top and then I come again and then I come again on this path, it will not happen. Why? Because simply imagine that as you are starting off, again, although this is a very basic of priority queue which you should know, but just a simple glimpse, that if you're starting from this specific cell, although always this is the minimum point to reach here. As you go on to this cell, okay, this is the minimum point to reach here, okay, as you go on to this cell, this is the minimum point to reach here. So as and when you are exploring the neighbors, you are always going on to a specific cell via the minimum path to reach that specific point. Even in worst case, let's say you would have explored, because let's say if you, there was, let's say okay, you explored this, then let's say you explored this, but let's say if the cost would have been now 1, okay, now let's say if you explore this thing, now here there's nothing outside, so you have to change it obviously for sure. So now there are 2 points, one is this, which your priority queue will have now. If these are the two candidates for the new priority queue, obviously the priority queue will pick up, let's say, this candidate based on whichever you picked first or how your priority queue configuration is, because now the cost is same, it's just that x and y are different. So let's say these are the two candidates right now. So even if you push any one candidate, either it can come like this to this point, or it can come like this to this point, or maybe from the bottom. So any which ways, if it comes to a specific point, it can come from the four directions: from the top, from the bottom, from the left, from the right. That is the reason a specific point, I, again, obviously, if let's say this would have been, again, like you might argue, Aryan, what if this would have been lesser cost, but if this would have come up, it would have been higher cost? No, because if this would have been a lesser cost, which means the arrow would have been pointing in that direction only. If it is coming from this path first, which means that out of the possibilities from these two candidates, it was giving him the lesser path. Again, all these were the basics of Dijkstras. If not, please go and watch the Dijkstras video. So This is the corresponding time complexity. Obviously, space will be O of m into n because again, I'm ignoring the constant terms, but it will be O of m into n. Again, you can add a constant, maybe 4 something of that sort. But again, ultimately, this will be the corresponding constant. Let's see the code. It's exactly same as what I told you, that we will have the direction. All the 4 directions which I have. Then I have the corresponding cost, again initialized by int max. Then I have the priority queue, which will make sure that it is on the basis of, again, as you can see, it will have the cost, it will have the x, it will have the y, but always making sure that it is on the basis of minimum cost. Same thing as I showed you in the code also. Then a simple priority queue, go and get the current cost, check for all the neighbors, make sure if the next cost is less, update the cost and update the priority queue. Simply return the final cost. Now, as I showed you, this is the corresponding time and space complexity. Now again, remove the constant, that is not required. Cool. Now, can you improvise this is a question. If yes, then how? Now, if you would have watched our previous videos, then we have learned a trick that is called as 01 BFS. This is mostly used along with Dijkstras. What this again, if you don't know this specific technique, please go and watch this video. Although I will give you a quick glimpse, but this is only the glimpse is only for those who actually know it a bit. Now, this says that obviously, if you look very closely to Dijkstras, Dijkstras is a single source shortest path problem, and that is the ultimate case of Dijkstras, which means that Dijkstras help us that if I have weighted edges, what if the problem would have been still same, single source shortest path problem, but for non-weighted edges, which means there are no weights, the best technique would have been BFS. Or let's say if I say single source shortest path problem with all same weights, then again BFS is actually the best approach. That is the reason you must be knowing the basics of BFS, that why BFS and where BFS can be used. Again, this video will tell you everything. So we realize that BFS is used for single source shortest path problem without weighted edges or with equal weights. And Dijkstras is primarily used for single source shortest path problem with weighted edges considering the weights are different. But this specific scenario which we are seeing right now, it has weighted edges. Obviously it has, because from this specific cell to reach here the weight is 0, but here the weight will be 1, here the weight will be 1, here the weight will be 1. So basically his problem is between BFS and Dijkstras. How? Because Dijkstras says weighted edges but different weights, and BFS says either non-weighted edges, or if weighted edges then same weights. So I am saying, okay, I have roughly same weights, I just have two weights, 0 and 1, that's it. So technically you solved it via Dijkstras, but can you leverage BFS considering you only have two weights? Yes, you can. Thus you can use a 01 BFS. 01 BFS says I only have two weights. Again, it is not necessary only 0 and 1 weight. No, I have two weights. I have at max two weights. In that case, still I can use a BFS. How? The 01 BFS simply says that instead of a simple BFS where you use a simple queue, in a simple queue, you push up new element and you simply grab out, like you just simply remove that element. That's how a simple queue works. 01 BFS says that considering you have to minimize the cost to reach final destination, earlier you were using Dijkstras. Dijkstras was saying that use or choose the minimum cost. Now, because we know the cost or the weights are only 0 and 1, we know that adding a weight 0 will incur no extra cost. Adding a weight 1 will incur 1 extra cost. If adding a weight 0, if it will incur no extra cost, which means the weight will remain same, which means the cost will remain same, which means that from this point, if I go to any another point, again, just imagine if I go to any another point, if the weight is 0, obviously the cost will remain same. Elsewise, if the weight would have been 1, the cost would have increased. So it is always beneficial to firstly take any specific edge which will give you a weight of 0. That is the reason I divided my queue and say, okay, I will divide this queue and use this specific queue by saying any weight of 0, any edge with a weight of 0, I will put up in the right portion of my queue. Any edge with a weight of 1, I will put up in the left portion of my queue. Thus, although in general you push and you pop from the corresponding queue, but what I will always try is I will always try to empty out my weight 0 first. Only when this is emptied entirely, only then I will try to empty out my weight 1 next. This is the essence of your 0 1 BFS. It says always try to use, obviously it's a queue, so it says always try to use your weight 0 first, because this will give you a lesser cost, and then if it is entirely finished, only then go towards using your weight 1. Okay, let's see how we will do it. Obviously, as we are pushing from the front, I know that in the front I have a weight 0. That is the reason I only need to push coordinates, which is x comma y. I don't need to push up the weight itself. Although you can do a different implementation in which you are pushing weight also, but as you can see, it is not required, because in the front you will always push up with the weight 0. In the back you will always push up with the weight 1. Now, let's see that how we will implement it, because the primary use case will be how are we popping and maintaining that firstly we are emptying the corresponding weight 0 queue. Because we have to push from both the ends, that is the reason we have to use a DEQ, right? And again, you might ask, Aryan, should I pop out from both the ends? Yes, you can do that also. But again, as I mentioned that, we can have different implementations for it. Let's see the implementation which we can have. Obviously, the things which will remain same is we will have directions. We will have the corresponding cost as a vector, and then I will have a DEQ. Now, as I mentioned that DEQ needs to only maintain the two coordinates x comma y. So I will maintain two coordinates x comma y, right? Then in the very beginning, I know that this specific first cell 0 comma 0 is only having the cost of 0. So I pushed it from the front, right? This cell 0 comma 0, and I will also say that the cost will nothing but be 0. Now again, exactly same how as what we do for a simple queue, or for what we did for a simple priority queue. Until my DQ is not empty, simply get me out the x comma y. As we get out the x comma y, we know that simply get out from the front. Now you might ask, Aryan, what if the front becomes empty? Oh, obviously it will never become empty, because front says that I am grabbing out the front, which means I'm grabbing out the weight 0. If it becomes empty, I will end up grabbing out from the weight 1, because technically it is a one single DEQ. So front is this also. If this is empty, then the front will start becoming this thing. Cool. So I will always grab out the corresponding front, and obviously make sure to remove it from the front also. So DQ dot top front. Now I will go on to the different directions, which means the directions is 0, the direction is less than 4, and then the direction plus plus. Obviously, same thing, that go to the new x, which is x plus the corresponding dir which we have, and then go to the new y, which is y plus the corresponding dir which we have, and then the new cost. Again, the same thing, that cost of x comma y plus, if the dir is not equals to my grid of x y minus 1, then just add a plus 1. Exactly same as what we saw above also. And same same if condition, that if I'm out of the bounds of the array, right, just simply continue. And again, in this if condition also, I can simply add that thing, that if the cost becomes lesser, again exactly same thing. If I go up here, I have put up this condition, right, this specific condition, like new cost condition, I can put up and merge this new cost condition here also. Again, it's totally up to ourselves. So again, when this is done, the actual crux lies in that the cost of new x and new y will become new cost, and then simply push it in the priority queue. Now, as I mentioned, putting in the priority, DQ, pushing in the DQ will lies on the fact that the direction. or basically the cost, the weight of that specific edge. Weight is nothing but for that specific edge, if the direction is not equals to my grid x y minus 1, which means that the weight is 1. If the weight is 1, push it from the back, dq dot push back, and I will just simply push up nx comma ny, right? Nx comma ny. While if it is actually of a weight 0, then I will push up in the front, push front, and just push up nx comma ny. And thus this is the only thing. So with this you are simply using a DEQ, and this is just a optimization on top of your above priority queue approach. Let's see the code. It's exactly very same as what I showed you right now. Exactly same of initialization, having a DEQ, having a DEQ, pushing up the corresponding node 0 comma 0 until it is empty, get out the first element, go on to all of its neighbors, making sure that find the new x, new y, find the new cost, making sure if it is under, like it is inside the grid, and also the cost is also less, then update the corresponding cost, make sure that you push back or front depending upon the weight was a 0 or a 1. Ultimately in the end you have the corresponding final cost. Because it is now simply mixture of Dijkstras approach along with optimization in terms of not using priority queue in general. Thus I will only have a space of O of m into, sorry, time of O of m into n, and space obviously will also be O of m into n, considering in the worst case you might push up all the elements inside your DEQ. Cool. I hope you guys got it. If you have any doubts in terms of 0 and BFS approach, if you want to go, try a bit more and go into a bit more deep, you can just go and watch this video. Maybe if you have confusion in Dijkstras, go and watch this video. If you have confusion in Dijkstras or maybe DP on grids, go and watch this video. Again, link all in descriptions. And again, if you have some approach, like some confusion on Dijkstras and go on to very deep, go and watch this video. Bye bye. Take care. I hope you guys got it. Again, this is actually a mixture of a couple of problems, and spatially in terms of time complexity. This is the actual problem which involve which will ask you to dig deep just to understand the complexity terms. Bye bye. Take care.